Hello, viewers. In today's session, we are going to discuss an important problem using Lagrange's mean value theorem. Right? So, here in this class, we are going to discuss this problem where we have to show that log of 1 plus x is equal to x divided by 1 plus theta x, where theta it lies between 0 and 1. And then using this result, we have to deduce this important inequality, that is x divided by 1 plus x is less than logarithm of 1 plus x, and this is further less than x for all x greater than 0. Right? So viewers, we have already discussed these type of problems in our earlier videos, but in this session we are going to make use of the second form of Lagrange's mean value theorem, which is slightly different from the first one. Right? So the usual form of Lagrange's mean value theorem is f prime of c is given by f of b minus f of a divided by b minus a. Right? So this is the usual form of Lagrange's mean value theorem, which says that if we have a function, say y is equal to f of x, which is defined in some domain, and if we take an interval, say a comma b, so this is a closed interval a comma b, and if this function it satisfies these two conditions, that is this function f of x is a continuous function in the closed interval, that is a comma b, and this function is derivable, that is f prime of x. It exists in the open interval a comma b. Then Lagrange's mean value theorem says that there must exist some number or some here quantity c which lies between a and b, such that f prime of c is equal to the quotient of fb minus fa and b minus a. Right? So this is the usual form of Lagrange's mean value theorem. So let us modify this form slightly by taking b is equal to say a plus h. Right? So now our interval is a comma a plus h. Right? And let us take a quantity theta which lies between 0 and 1. So now the Lagrange's mean value theorem says that a function f of x is defined in some domain, and if we take this interval, that is a comma a plus h, where b is equal to a plus h. Right? So now we'll express Lagrange's mean value theorem in terms of theta and h. So f of x is a continuous function in the interval, that is a and a plus h. Right? So now we are using for b a plus h, and this function f of x, it is differentiable, that is f prime of x exists in the open interval, that is a comma a plus h. Then there must exist a point c, that is which lies between a and b. So here b is a plus h. Right? So now this number c is given by a plus theta h, where theta it lies between 0 and 1. Right? So the second form of Lagrange's mean value theorem says that if we have a function y is equal to f of x, which is defined in some domain D, and if we take an interval that is a comma a plus h, and if f of x is continuous function in the closed interval a comma a plus h, and the function f of x has derivative, or it is differentiable in the open interval a comma a plus h, then there must exist a real number, or at least one number theta, such that theta lies between 0 and 1, and this c is given by a plus theta h, right? So then we can now write the Lagrange's mean value theorem as f prime of c. So c is a plus theta h, and here we have f of b. B can be replaced by a plus h, and then we have f of a, and b minus a can be written as a plus h minus a, right? So let us simplify it. So we have f prime of a plus theta h is equal to f of a plus h minus f of a divided by h. So this a and this a get cancelled. So let us multiply this quantity with this h. So we have h, and f prime of a plus theta h is equal to f of a plus h minus f of a. Now taking f of a to the left hand side, we have f of a plus h f prime of a plus theta h, that is equal to f of a plus h, right? So Lagrange's mean value theorem in second form can be expressed by this equation, that is f of a plus h is equal to f of a plus h and f prime of a plus theta h. So this is known as the second form of Lagrange's mean value theorem, where this quantity theta, it lies between 0 and 1, right? So in the second form of Lagrange's mean value theorem, if these two conditions are satisfied, then there is at least one number theta such that theta lies between 0 and 1, and f of a plus h should be equal to f of a plus h times f prime of a plus theta h. So let us make use of this equation to solve this problem. So now consider a suitable function, say y is equal to f of x, that is equal to a log of 1 plus x, right? And here we are using the notation that is log for the natural log. So we can also write natural log of 1 plus x. So here the base of the logarithm is the exponential number e, and here we'll prefer this notation. So we are considering this function y is equal to f of x is equal to log of 1 plus x, which is defined in some domain, and let us take the interval as 0 comma x. So here this is a closed interval, and here x is greater than 0, right? And we can see that this function, it satisfies the conditions of Lagrange's mean value theorem, that is a log of 1 plus x. This function is continuous in the closed interval, that is 0 comma x for all x greater than 0, and this function, the derivative of this function exists in the interval, that is the function f of x is derivable in the interval, open interval 0 comma x, right, for all x greater than 0. So the two conditions of Lagrange's mean value theorem are satisfied by this function, and now there must exist at least one theta which lies between 0 and 1, such that f of a plus h is equal to f of a plus h times f prime of a plus theta h, right? So where the interval is a comma a plus h. So let us compare this interval with this one, right? Because this equation is for this interval. So if we compare these two intervals, then we can see that the value of a is equal to a 0, and a plus h can be written as equal to x. So a is 0, so here we can write 0, so we have 0 plus h is equal to x, so h is equal to x, right? So we have a is equal to 0 and h is equal to x. So let us replace a is equal to 0 and h is equal to x in this equation. So we have f of 0 plus x, and then we have f of 0, and then we have x for h, and f prime of 0 plus theta x. So what we have done, in this equation we have replaced a by 0 and h by x. So now let us simplify it. So we have f of x, 0 plus x is x, f of 0, and then we have x times f prime of theta x. So this is an important equation. Now let us again come to this function f of x is equal to log of 1 plus x. So let us differentiate f of x. So f prime of x is given by d by dx of log of 1 plus x, and the derivative of log of 1 plus x is simply 1 over 1 plus x, right? So now here we need to find out f prime of theta x. So let us replace this x by theta x. So f prime of theta x is given by 1 over 1 plus x is replaced by theta x, right? And let us find out the value of f of 0 by taking x is equal to 0 in this function, right? So we have log of 1 plus 0, that is equal to log of 1, and log of 1 is equal to 0. So now we have f of x is equal to f of 0. Here we have f of 0 is 0. Then we have x times f prime of theta x, and f prime of theta x is 1 over 1 plus theta x. So this is now simply x over 1 plus theta x. So f of x is equal to x over 1 plus theta x, and f of x is given by a log of 1 plus x. So we have this result, that is log of 1 plus x is equal to x over 1 plus theta x. So this is how we can prove the first part, where theta is it lies between 0 and 1. Now let us prove this inequality with the help of this result. So now to get this inequality, let us start with this one, right? So we have theta lying between 0 and 1. Now let us multiply throughout this inequality by x, right? And the direction of the inequality, it remains the same, because we are taking x greater than 0 and x is positive here, right? So here we have 0 times x, here we have theta x, then we have 1 times x. So 0 times x is 0, and here we have theta x, and here we have x, right? Okay. Now let us add 1 throughout this inequality, because here we need to find out 1 plus theta x. So let us add 1 throughout. So here we have 1 plus 0, here we have 1 plus theta x, and here we have 1 plus x, right? So 1 plus 0 is 1, and here we have 1 plus theta x, and here we have 1 plus x, right? Okay, now let us take the reciprocal of all these three numbers. So we have here 1 over 1, here we have 1 plus theta x over 1, and here we have 1 plus x over 1. So let us take the reciprocal of all these three quantities. So we have here 1 over 1, here we have 1 over 1 plus theta x, and here we have 1 over 1 plus x. And remember, whenever we take the reciprocal, the direction of the inequality, it gets reversed. So here the direction of the inequality is like this, right? So now we have this inequality. So here we have x over 1 plus theta x. So let us again multiply throughout by x. So let us multiply these three quantities by x. And remember, x is greater than 0. So now here we have x times 1 over 1, then we have x over 1 plus theta x, and here we have x over 1 plus x, right? So we have x, and here we have x over 1 plus theta x, and here we have x over 1 plus x. Now x over 1 plus theta x is given by a log of 1 plus x. So we can now write here for x over 1 plus theta x as a log of 1 plus x, and here we have x, and here we have x over 1 plus x. Now let us rewrite this inequality by writing x over 1 plus x, and then we have log of 1 plus x, and then we have x, and this is our required inequality for all x greater than 0, right? So viewers, this is how by making use of the second form of Lagrange's mean value theorem we can solve this problem.